All right. Good evening, class. How's everybody doing today?
Good.
All right. Good. Today's lesson, ladies, we'll be going over water versus oil. All right. Now, we all know that water and oil don't mix. All right. But why is that? Well, let's look at a few differences between water and oil. Well, as a molecule, water is a polar molecule, meaning that it has a positive and a negative charge. Well, we know that opposites attract, so when water molecules, the positive end sees the negative end, then they attract to one another. However, oil is a nonpolar molecule, meaning that it does not have a charge. So that's why it's not attracted to water at any point. Water, the very dense molecule, meaning that the molecules are tightly packed together. So when oil tries to, of course, unite with it, it's unable to because oil molecules are fewer molecules per any unit of measure. So if we were to take a cup of water and a cup of oil, the cup of water will have more molecules than the cup of oil will. All right. So, and here are some basic differences between the two. Of course, chemical formula. If you look here, C18, H34O2. Oil has a lot more inside of each molecule than water does, which is simply H2O. All right. Molar mass, you see that oil is much heavier, and density, you'll see that oil is less dense than water. All right. So now, what we're going to do in today's lab, we're ultimately going to take this principle and we're going to make a lava lamp. I know everybody loves a lava lamp. They're real popular back in the 60s and 70s, but we're going to make one today. All right. So the first thing that we're going to do, we're going to have to pour 3/4 cup of water into our bottle. All right. So we'll use the cold pitcher of water. We'll use the measuring cup, and we'll use the funnel. If y'all will, you can sit your binders on the floor so it gives you just a little bit more space to operate. Now, as Derinique goes through with our experiment, all right, we're going to take a quick look at some of the questions down here at the bottom. All right, walk the camera forward if you will. All right, as she measures out 3/4 cup of cold water to get ready to pour into our bottle, let's look at some of the questions that we have here. All right, does temperature of the water affect the reaction? Well, we're going to see that by utilizing cold water first and warm water second. Does the size of the bottle affect how many blobs are produced? Well, each of the students here has a different size bottle. One has a 2-liter bottle, one has a 1.75-liter bottle, and one has a 1.25-liter bottle. Does the effect still work if the cap is put on the bottle? We'll see that on our second try. And does the size of the tablet piece affect the number of blobs? We'll notice that as we enter different size Alka-Seltzer tablets into our solution. All right, so as we continue to move forward, now as the water goes around, let's use the oil using the same funnel each time. All right, now we're pouring the oil until it fills all the way up to the red line. Now, with the bottles being so tall, if you need to, students, you are welcome to stand up as you prepare to pour. A little bit more. There we go, that'll work. All right. So now, as we continue on throughout the experiment, the first thing that we're waiting on is for the water molecules and the oil molecules to separate. Now, of course, it's a fascinating process. Once again, the many reasons why oil and water don't mix. The polar water molecules will eventually migrate to the bottom of the bottle, while the more dense molecules of oil rise to the top. Oh yeah. Don't worry, we have a backup bottle of oil that we will be using if need be. Now, it may take a few minutes for our oil to separate, which is why we're working in shifts. So by the time we finish the last fill up, we should be ready to add our food coloring to our first bottle. All right, that's good. All right. We'll need a backup bottle of oil. Now, once Alina finished, if you will, Darren, pick any one of the food colorings, and we're going to add 10 drops of food coloring to your bottle. And once she finished, we'll work our way around. All right, you hold on to yours. Just a little bit more. All right. Now, D, what's food coloring color?
Uh, what?
We have green, red with a yellow
Green.
cap.
Well, that's yellow.
All right. And we have blue and green left. So, but wait till your water fully separates.
Okay.
Alina, D, you should be good to go ahead and drop your food coloring in. Now, Darren, all right, go ahead and find half, as close as you can to half a tablet of Alka-Seltzer and drop it away inside your bottle. That's good. All right, let's drop it and let's see what's going to take place here. As it begins to dissolve, we should see the food coloring bubbles begin to rise. And as those food coloring bubbles begin to rise, we now create the essence of our lava lamp using the principle that water and oil just don't mix.
Oh, that's neat.
Now, what's causing those bubbles to rise is the Alka-Seltzer tablet dissolving, releasing gas bubbles up to the surface. Now, the question that asks us, will the cap work? Will it work if the cap is still on? Well, my theory is that it will just take place longer because now those gaseous bubbles aren't going to be released because the cap is on. So, if one of y'all would utilize your cap when you prepare to add your food coloring droplets and your Alka-Seltzer tablet, we'll be able to answer that question.
Okay. Is there a certain size I need to get? Small one again?
Go with the half first. All right, so let's see the results. If the cap is on, will it still work? And how long will those bubbles last? And as we see, the first few bubbles flow back down to the bottom.
Mm-hmm.
Case in point, proving the theory correct that with the top on, those bubbles are not able to be released. So now we can see a juggling effect of those gaseous bubbles and the food coloring trapped inside. Now, if we come back and look once again at the first bottle, we see that even though it is a smaller bottle, it is still producing nearly the same amount of gaseous bubbles as the larger bottle is. Henceforth, going back to one of our key questions, that the size of the bottle is really not playing a significant role in the number of bubbles that it's producing. All right, and the last bottle. Now, with this situation, let's go with a smaller piece of Alka-Seltzer tablet to see if we'll still get the same amount of bubbles and the same results. Got 10.
That's 10. That was 7.
There
One
we go.
more. Was that 10? That was 10. Okay.
All right. So now with this last bottle, we will use a smaller piece, whereas the first two bottles, both each use half a piece of Alka-Seltzer tablet. Now let's go with a quarter of Alka-Seltzer tablet. Let's see if you can find one that'll work. Now we'll leave the top off and we'll see the effect. Now, my theory is the smaller tablet means that it's going to produce less bubbles because there's not much tablet that will be dissolved in this situation. Will it still produce bubbles? Yes. But the time period that it produces bubbles will not be nearly significant enough as the half a piece used simply because the pieces are larger. Now, let's try something as well. D, with your bottle, since you had the top on, let's give it a little shake or turn it upside down and set it back normal. Well, there you have it. The true effect of the lava lamp.
Yeah.